definite integral that involves a floor function. So let's briefly review what that means. Now the floor function or the greatest integer function, I'll just pick the numbers 8.2, let's say, and the floor of that is equal to 8, all right? And you can think of the floor function as being the number minus its fractional part. Okay, now it's not a rounding function because this is also equal to the floor of 8.7, okay? Now the thing to note here, why these two numbers share the same floor, is they both exist between 8 and 9. In other words, 8 strictly less than 8.2, comma, we'll delineate with commas, 8.7 and 9. And notice that 9 is the successor or the increment of 8, all right? And that's really what distinguishes elements. That's how things get to have the same floors if they're between the same two consecutive integers, okay? 8.2 and 8.7 are between 8 and 9, therefore they have the same floor of 8. Okay, now that kind of reasoning is going to come to play here when we actually attempt to evaluate this integral. Now, again, one last comment. The floor of any expression whatsoever, okay, is guaranteed to be an integer. And let me just say member of Z. All right. Now, what's so special about that? Well, you guys have done integration. It's trivial to integrate a constant function because you're just finding the area of a rectangle, and that rectangle has height equal to the constant and a width equal to the difference of the limits of integration. Let's get busy trying to solve this particular problem. Now, y'all, it makes sense to consider what's going on between 10 and 11 because that's part of the limits of integration. That's a sub-interval in these limits of integration of 7 and 11. Now, this inequality is very easy to establish. You know, if you plug 10 in here, you would get 60 over 15, which is 4. Now, this is an increasing function. That takes a little bit of explanation. You have a vertical asymptote at x equals -5, and the graph goes up after that. But anyway, we'll just make that assumption. Now, notice here, this is 6x over x plus 5 is the radicand here. Okay, it's inside a radical. And so notice that the floor would be connected to the square root of 4, which is 2, and the square root of 5, which is a number less than 3, right? Okay, so for that reason, we can conclude that the floor of any number between 10 and 11, the floor of any number in the interval 10 and 11 is going to be the 2 that you see right here. And as I said before, this is easy to integrate. The answer is just 2. And again, just think of a rectangle of height 2, width 1, okay? The antiderivative here would be x. You could evaluate it, but again, it's easier to think of this just geometrically as the area of a rectangle. All right, now similar reasoning will lead to this truth right here for x between 7 and 10, and notice that's the other part of the limits of integration. That forces the 6x plus x over 6x over x plus 5 to be trapped between 3 and 4. And so notice the square root of 4 is, again, it's less than 2. I mean, the square root of 4 is equal to 2, excuse me. Square root of 4 is equal to 2. All right, but you see, that would mean that the floor, if 6x plus 5, if the quotient 6x over x plus 5 is trapped between 3 and 4, that means it's going to have a floor of 1. Okay, because when you take the square root, you get numbers between 1 and 2. Okay, so what we end up with right here is the integral from 7 to 10. And again, now we can replace the floor of the square root of 6x plus 5 with just 1. And I'll write that for emphasis. We'll write down 1 dx. Again, folks, if I went a little too fast there, it didn't make any sense the way I said things. If 6x over x plus 5 is trapped between 3 and 4, which it is on the interval from 7 to 10, the square root of 4 is 2, all right? And square root of 3 is a number still bigger than 1, right? And so the floor of this expression, as long as x is in this interval, is going to be 1. Now, I'm not writing that down. I'm just writing it down in this form. I replaced the floor of the square root of our expression of interest here with 1. And then we already know that this part over here is equal to 2, right? We just did that on the previous line right up here. Okay, so that's equal to 2. And so what you get right here, you have a rectangle, height 1, with a width of 3. And so we end up getting 3 plus 2 here. Final answer. 3 plus 2 is equal to 5. So in some sense, these integrals involving floor functions are going to be easier because the floor function evaluates to an integer and the integer of a constant is trivial to find. However, you do have to work with inequalities to determine on what ranges of, on the subranges of the limits of the integration, what the floor function is going to be in those subranges. Okay, so that's the part that's, I wouldn't call it hard, it's just some tedious work. Anyway, the final answer is 5, so let's come back up here, complete this thing. Hope you liked it. Let me know what you thought.